Welcome again, and this is part 3 of Module 8. So, for this module, we will be discussing atomic spectroscopy, both the absorption and emission based techniques. Okay, so the process of atomic spectroscopy starts with the conversion of your analyte into free atoms. Okay, so this is very important, no? Because as we've learned from the theoretical aspects of spectroscopy, different chemical species will exhibit different interactions with electromagnetic radiation. So if you're doing absorption or emission measurements, the emission and absorption profiles for free atoms would be very different for that of molecules or of ions. Because remember, the absorption or emission of radiation is based on the energy levels contained in that particular substance. Okay, so if you start with a usually the sample is converted into a solution type. Okay, so the instrument for atomic spectroscopy would have parts or components that would allow for the nebulization. So when you say nebulization, you convert the solution into a fine spray, which by usually heat, you dissolve it. Okay, so you remove the solvent, so what you now have is the dry aerosol. And again, with higher temperature treatment, we would be able to volatilize the analyte in the dry aerosol to become free atoms. Now, as you've learned from atomic spectroscopy, common interference in this technique would be the conversion of the analyte free atoms into either molecules or ions. Okay? So, as you will see later, the different techniques used in atomic spectroscopy are done to ensure the that the analyte is in its atomic form, and not transformed into molecular or ionic forms. So this is the schematic diagram for a flame AAS. So as we discussed in the previous modules, so you have here the same components. So you have here the light source, you have here the wavelength selector, and then you have here the detector. Now, although it's not quite obvious, the sample holder for AAS is actually the flame, coming from the burner. So the flame actually holds the analyte in its free atomic form. Okay, so yun yung kailangan tandaan lagi for AAS, It's important that your analyte is converted into its free atomic form. Okay, so as you can see from this setup, this is actually a double beam setup, So you have here a beam chopper. All right, so from the beam chopper, you divide the incident light. The first half goes through the flame, the sample holder, while the other one goes unimpeded. All right, through an optical pathway towards the monochromator and the detector. So since this is based on absorption, okay, as we discussed earlier, this is still based on the measurement of transmittance. So you need to get the power or intensity of the incident beam and compare that with the intensity or power of the transmitted beam, the one that passed through the sample. So in Flame-AAS, the flame is very important because it's the one that converts your analyte into free atoms. Okay, and if you remember from your general chemistry, you actually need 3 components to create a flame. You need a fuel, an oxidant, and of course a heat source, to ignite or to initiate combustion. All right. Now, in flame AAS, the temperature of the flame is also important. Okay, um, the the factor that we consider in choosing the type of flame to use actually depends on the element that you are analyzing. Okay, so here are some examples, no, of different flame types. No, so first you have your low temperature flame. All right, roughly the temperature is around 1750 to 1850 degrees centigrade, and the usual fuel is propane or natural gas plus air or oxygen as your oxidant. And this is suitable for alkaline and alkaline earth metals, so sodium, lithium, potassium, calcium. So why low temperature flame? Because these elements, these metals are actually easily ionized. Okay, we explained earlier that it's important that your analyte remains in its atomic state. So if it ionizes because of a higher flame temperature, then you are converting most of your analyte into ions, okay, which will not give you the expected response or sensitivity as you would get with free atoms. All right, so that's for low temperature flame. The more common is your medium temperature flame. Okay, and this is what we have in the laboratory at the chem lab at Adams University. All right, so what we're using there is a combination of acetylene as fuel, no, acetylene gas, and air from compressed air. And the temperature is roughly between 2200 to 2400 degrees centigrade. And this is convenient to use, no, for most elements, even for alkaline, or sorry, not alkaline, alkali or alkaline earth metals. Okay, you just need to control the ratio of the fuel and the oxidant so that you can minimize the temperature at the lower end, no? And so this is quite suitable for most elements except for aluminum, selenium, and alkaline earths, no, and vanadium. Okay. The problem here for aluminum and selenium is that they form what you call refractory oxides, no. So refractory oxides are very stable oxides. Okay. So for those cases, you need higher flame temperatures, no. So there are higher flame temperatures, no, wherein you use hydrogen gas as your fuel. Okay. Now for the medium flame, if you need to increase temperature, then you can add another oxidant, no, your nitrous oxide, no, which is a powerful oxidant, no. So if you're familiar with Fast and the Furious, you've been hearing this nitro, no. So nitro or nitrous oxide actually is actually an oxidant, okay, which enhances the combustion of your fuel. All right, so leading to higher flame temperatures. Okay, so with the flame AAS, what are the things that we need to optimize? So first, as we shown earlier, you need to optimize the type of flame, okay, because the combination of the fuel and oxidant will determine the temperature of the flame. Okay. Also, you need to optimize the fuel and oxidant flow rates. Okay, the ratio between the fuel and the oxidant, because number one, this will determine also the temperature, the resulting temperature of the flame. And another is that if your fuel and oxidant flow rates are too fast, the tendency of the flame is that it will go out. Okay, hindi magi-ignite yung flame. Also, if your fuel and oxidant flow rates are too slow, then there is the danger of what you call a backfire. Alright? So this happens when the flame, instead of bursting out of the burner head, it ignites inside the premix chamber. So it's very dangerous. But not to worry, no, because all AAS systems are equipped with safety measures, okay, that will protect the system from backfire ignition. Okay, so wala pang kaso na may AAS na sumabog ever, no? Uh, Kasi nga uh, the manufacturers make sure na safe, no, yung ating equipment. Now, two parameters here, okay, in relation to your burner orientation. So you have your burner height and the burner alignment. So maybe we can draw this one. Okay. So here, no? So again, if you have here your light source, your hollow cathode lamp, I'm just trying to simplify the illustration. Then you have here the detector. Alright. Alright. So the burner head, okay, so ito yung flame, okay, this can actually be adjusted, alright, vertically. Okay, so you can lower this down or raise it up. Alright. Now, the importance of that procedure is for you to set which part of the flame will the light, no, or the radiation coming from your hollow cathode lamp will pass through, okay, as it goes from the source towards the detector. Okay, and if you remember from your general chemistry, when you studied your Tyrrell burner and the parts of the flame, your flame actually has the blue flame, no, actually has three parts, no. So you have your inner cone, you have your outer cone, and this intersection here is very important. This is what we call your interconal region, and we know that this is the hottest part of the flame. Okay, now in relation with AAS, the interconal region being the hottest means that this is the region where you have the most free atoms. All right, you have the most free atoms available, no, in the flame. Okay, and the other parts of a flame are what we call the reducing part and the oxidizing part. All right, so changing the burner height will allow you uh, um, to maybe get the information, no, about the analyte from different regions ng flame. Okay, now here are some examples, no, of the importance of adjusting the burner height, no. So you have here three elements. So you have magnesium, silver, and chromium. Now if you look at silver, okay, as you increase the burner height, okay, what happens? The absorbance increases. Why? Because as you go higher, so when you say burner height, you are going higher, no, dun sa part ng flame. Okay, because as you go up, okay, the flame, you get more and more silver free atoms. Okay, you don't encounter problems with silver atoms because silver atoms do not uh, interact with oxygen gas, no, so it doesn't form refractory oxides. Okay, and that is actually the case for chromium, no. As you can see, for chromium, baligtad yung trend, no. So as you increase the burner height, the absorbance decreases. Why? Because as you go up the flame, all right, chromium, okay, reaches the oxidizing part of the flame, wherein it can interact actually with oxygen to form refractory oxides. So when you say refractory oxides, these are molecules, no, molecular species that are hard to break down into free atomic forms. Okay, and this causes a decrease in absorbance because you are reducing the amount of free chromium atoms. For magnesium, Okay, as you can see, you have here a some sort of parabolic trend. Okay, why? As you increase the burner height, you're going to the hotter part of the flame. You are producing more and more magnesium free atoms. But as you go further towards the oxidizing part of the flame, you are now forming the refractory magnesium oxide. No? So again, refractory, it means to say that it's hard to um, call this hard to break down, okay, into free atoms. Okay, so let's erase this part here. Now, how about burner alignment? Okay, burner alignment is related to your cell path length. Okay, so what do you mean by cell path length? So again, if you go back to Beer-Lambert's law, you have absorbance is equal to, let's use epsilon BC. So the cell path length, okay, refers to the um, distance, no, or the diameter that your light or your radiation passes through, okay, wherein this length contains your analyte. Now, in UVV spectroscopy, the cell path length is controlled or can be controlled by choosing the diameter of the cuvette that you are using. Now, in Flame-AAS, since the the flame is actually your sample holder, alright, you can actually tilt, okay, you can actually tilt the burner head, okay. Now, if you're orienting it this way, you are allowing light to pass through the whole length of the flame. So, in this case, you are doing your measurement at maximum cell path length available for this particular burner head. But if you're going, say, to, how can I draw that one? Dito na lang. Okay, so now if we're going to tilt, I apologize for the drawing. No? So if you're going to tilt the flame, okay, you are able to reduce, no, the portion. So ito lang yung portion ko, no? You are going to reduce the portion of the flame, of the flame where the radiation interacts with. Unlike here sa baba, no, your radiation interacts with the full length of the flame. Here, since you tilted the burner head, you reduce, no, so you lower down your cell path length. And this technique is useful actually if your samples are quite concentrated with the analyte. So instead of diluting your sample, what you can do is you can reduce the cell path length by simply tilting the burner head. Now, for most AAS systems, you can actually replace the burner head if you want. No, you can choose a smaller burner head or a larger burner head. Okay, depending on the requirements, no, of your analysis or your sample. So here are some of the features, advantages, and disadvantages of your Flame AAS. No? So first, this is quite reproducible. Okay, this is one of the major advantages of Flame AAS over the older turbulent type burners. No, it's very reproducible. However, not efficient. Why not efficient? Because if you were able to do AAS, no, back at the laboratory, you would notice that for the Flame AAS, you're actually aspirating your sample solution, all right, no, into the nebulizer and into the flame. Now, not all of the solution aspirated will actually end up with the flame. No, only about less than 10%, okay, of the solution goes to the flame, and the rest just goes to waste. Okay, so medyo sayang siya, no, sa sample. Okay, so that's one of the disadvantages, but it's very reproducible. All right, and in relation to that, it's sample consumptive. No? Since you are just throwing away majority of the sample aspirated, then you're wasting your sample. Okay. Another problem is that there is a shorter residence time of atoms in the optical path. Okay, unlike in UVVs, though you're using cuvettes, your analyte will just stay there, right? But for Flame-AAS, since your atoms are actually freely moving away towards the flame. Okay, so that's the reason why during the analysis you need to continuously feed the flame with your sample solution. No, bawal mong tanggalin yung aspirating tube, no, doon sa iyong sample solution. All right. Advantage would be fast atomization. No, once your sample solution gets into the flame, then you have your analyte atomized readily. All right. It's cheaper, okay, compared to the another system that I will be showing you in the next slide. So Flame-AAS is quite cheap. Actually, the AAS system that we have at Adamson, no, it uses a flame atomizer. It cost us around less than 2 million, no, 2 million or less than 2 million. So it's quite cheap. All right. Alright, so shown here is another common atomizer for your AAS system. You call this your electrothermal atomizer, or also called your graphite furnace. Okay, so the graphite furnace, so shown here, is actually a tube, alright, that is electrothermally heated. So remember that graphite is electrically conducting. Okay, so by using some electronics, you can electrically heat up your graphite furnace, okay, and your sample is actually placed inside the furnace. Okay, so the increase in the temperature of the graphite furnace causes the atomization of your analyte. Okay, now for the electrothermal atomizer, it is actually done in a series of steps. So you need to program the temperature of the graphite furnace, no, and you need to do it in a series of steps. Okay, so you need to do temperature programming. So first you do a drying step. All right, why drying? One advantage of electrothermal-AAS or electrothermal atomizer is that you can actually analyze solids and liquids directly. All right, so you are doing away with sample preparation, and that's one of the advantages, no, of your graphite furnace AAS. So since you're placing here a solid or a liquid sample, the first step is to remove water. All right, so drying step, no, around 110 to 120 degrees centigrade, followed by charring step. In the charring step, you are increasing the temperature from 600 between 600 to 1000 degrees centigrade, and the purpose of which is to remove combustible organic compounds. All right, because, well, usually for AAS we're interested with the inorganic, no? Our analysis on inorganic element. Then following charring, you now have your atomization. So here you rapidly increase the temperature between 2000 to 3000 degrees centigrade, and this is where the analyte is converted into free atoms. So the free atoms will reside, no, inside the graphite furnace. Okay, and your light will pass through this way. All right, so it will the light will, or the radiation will interact now with your free atoms. So after the atomization step, you now have the cleaning step, the purpose of which is to remove any residual sample, okay, present in your graphite furnace, so that after which it will be ready for the next sample. Here are the features, advantages, and disadvantages of your graphite furnace or electrothermal atomizer. First, it has enhanced sensitivity. Okay, and the entire sample is atomized. Okay, since you are placing directly your sample, no, and one advantage of Electrothermal-AAS is that you can directly analyze solid or liquid samples. So you can just place there your soil sample or your blood sample. No, you just need a few microliters of your blood sample, no, to be analyzed. Now, so the whole sample that you place in the graphite furnace will actually be atomized, no, fully atomized. Now, enhanced sensitivity, why? This is because of the greater residence time of atoms in optical path. So the graphite furnace actually traps the free atoms during atomization, okay, wherein your radiation can interact with it more. So the longer this interaction is, you are actually enhancing the sensitivity of the method. Okay, so this is one of the best advantage, no, of electrothermal AAS compared to flame AAS, no. And of course, no, yun nga, wala ka ng sample prep because you can directly analyze your sample sa graphite furnace. However, a disadvantage would be a slow atomization process. So if you recall, you need to do some temperature programming. You need to ramp up the temperature slowly. Then after finishing the temperature program, you need time to allow the furnace to cool down before you can place another sample, no? So you have you have longer analysis time, no, when using graphite furnace. And then finally, it is actually more costly, no? It's more expensive to equip your AAS system with a graphite furnace compared to using just the Flame-AAS. But most, if not all, AAS systems are actually modular in or by design. Okay, so if you equip it with flame atomizer, then next time you decide to use a graphite furnace, then it's okay. You just call the technician, just remove the flame setup, okay, and then attach the graphite furnace module, and then you can revert back to the flame atomizer setup, no? So it's modular by design. Okay, so next let's discuss your interferences, no, for AAS. So there are actually two types of interferences. You have your spectral interferences and your chemical interferences. For spectral interferences, this refers to anything that will um, co-absorb radiation from the hollow cathode lamp, okay, or from your light source. Okay, so usually common spectral interferences would be if you're using flame AAS, then the flame itself, no, if you notice, your flame is actually quite luminous, all right, and this is due to molecules, no, or molecular species that is present in the flame, no. So these molecular species come from your fuel, no, the combustion of your fuel, and also these interferences may also come from the sample matrix, okay, the matrix of your sample. All right, now what you have to remember for spectral interference is this, no, the total absorbance, no, AT, the total absorbance detected, no, or quantified by your AAS system actually comes from two sources. All right, so it comes from the absorbance of the analyte itself and the absorbance coming from the background, no. So yung sa background may come from the flame or coming from the matrix components. Okay, so in remedying spectral interferences, all you have to do is to find a way as to remove your background absorbance, no. So subtractive lang ito in nature. So two common ways. So the first one is the use of a continuum source. All right, In this case, we use a deuterium lamp. Ito yata yung meron tayo sa Adamson. No? We call this your D2 correction or deuterium lamp correction rather. So here, you're using two lamps. No? So you have your hollow cathode lamp. Alright? Nakalimutan ko sabihin sa unang slide. No? Aside from hollow cathode lamp, you can also have your electrodeless discharge lamp. No? So these are the two common light sources, no, for AAS. Alright, so here you have your hollow cathode lamp and you have here your deuterium lamp. Okay, now the purpose of your deuterium lamp is to measure the absorbance of your molecular species. Hence, you are measuring the absorbance of the background. Whereas the absorbance computed from the hollow cathode lamp measures the absorbance, the total absorbance. So since now your system, you're able to distinguish between the total absorbance and the background absorbance, then you just need to subtract this from the total absorbance so that you can get your absorbance for the analyte only. Alright, so ito yung technique, no, sa spectral interferences. Well, another more expensive way is by using what you call the Zeeman effect. Okay? So, medyo mas mahal yung unit na mayroong Zeeman effect. So, here, what you do is you actually have magnetic plates, no? Okay? Electromagnets, alright, that is placed in between your atomizer, whether that's graphite furnace or flame. Alright? And the magnetic field is actually turned on and off, okay, in some sort of pulse, no? So naka-pulse mode siya. Now, when the magnetic field is off, okay, what your detector is measuring is the total absorbance. Okay? Whereas when the magnetic field is on, what your system is measuring is just the background absorbance. So again, subtracting the two, you will get the absorbance for the analyte only. So this is what we call your Zeeman technique or Zeeman effect, no, for removing spectral interferences. Now, if you're interested in knowing more about this, you can read this up, no, in your textbooks. Next, you have your chemical interferences. So this pertains to anything that reduces the amount of atoms due to the formation of the competing species, no? Yung ionic sa molecular species. So again, the objective sa AAS is to convert your analyte into free atoms, no? And nagko-compete yung formation ng ions and molecular species. Alright? So what are the ways to reduce chemical interferences, no? First is for alkali and alkaline earth metals, no? So they are very prone to ionization. So what you can do is to use an ionization suppressor. Alright? So for example, if you're analyzing potassium, alright, then you can add a little bit of cesium. So why does cesium act as an ionization suppressor for potassium? Because cesium has a lower ionization energy compared to potassium, if you remember your periodic trends. Meaning to say that cesium will actually get ionized first before potassium. So you are sacrificing cesium here. Alright? So that you can prevent the ionization of potassium. Alright? So if you're analyzing for sodium, then you can add potassium as your ionization suppressor. Because again, potassium would be easier ionized compared to sodium. Another is to solve the problem of refractory compounds. Okay, so again, refractory compounds are those compounds, molecules that are difficult to break down. A common example is for the analysis of calcium. Okay, calcium actually, quite stubbornly forms calcium phosphate. Alright, and this compound is actually very difficult to atomize, no, using your flame. So what you can do is to use a releasing agent, and a common releasing agent for calcium analysis is the addition of lanthanum ions, no, from lanthanum nitrate. Why? Because lanthanum has a higher affinity towards phosphate, no, sorry, not towards phosphate compared to calcium. Alright, so what will lanthanum do is to steal away phosphate so that calcium will be liberated. No? So this is what you refer to as a releasing agent. Then lastly, you can use a protective agent. No? So this is to prevent your metal analyte from forming unwanted refractory compounds in the first place. So usually protective agents are chelating agents. No? So an example would be the use of 8-hydroxyquinoline for the analysis of zinc. Alright, so with 8-hydroxyquinoline, you are chelating zinc to form an organic complex, no, or an organic chelate. So once this chelate goes through the flame, the organic component, the organic ligand or chelating agent will just be burned away, liberating your zinc. Alright, so this is your an example of a protective agent. Alright, so for this part of the module, we're going to discuss some of the sample preparation techniques for AAS, most especially for flame. AAS, sabi nga natin, for graphite furnace, you have no to minimal sample preparation. So again, the objective, no, in general, no, of sample preparation is basically to liberate your analyte from the sample matrix, okay, and to convert your sample into a form which can be processed by your analytical method, whether that is classical or instrumental. And as you've noticed, the most convenient form of this for the sample is the solution form, no? Kaya nga karamihan ng analytical methods ay naka-based sa analysis ng sample solutions. Okay? So some of the common sample prep techniques, no, for AAS. So first, you have your wet ashing. So sa wet ashing, ito yung digestion na tinatawag ninyo in some practice. So this involves the use of acids, no, concentrated mineral acids, no, such as HCl, sulfuric acid. Sometimes you need to use hydrofluoric acid, no, if you're doing away with silicates, okay, or sometimes you need to use mixtures of acids, no, such as your nitric acid, no, yeah, nitric plus sulfuric, or minsan yung aquarehia na tinatawag. Okay, so and usually you need to apply heat, no, digestion, no. So the acids actually eat away the sample matrix, no, making your sample soluble, no. So after digestion, you dilute the resulting solution in some amount of water. Okay, dry ashing is a little bit different because here you first pyrolyze, pyrolyze, no? So you pyrolyze first your sample. So when you say pyrolyze, you burn your sample inside a furnace. Okay, so usually you do dry ashing, no, for organic, no, organic based samples, so such as leaves, for example. So after pyrolyzing, you will get the ash, okay, and you dissolve this ash in acid also. Okay, so the ash would contain mostly inorganic material. So during the pyrolysis part, you are removing the organic component of your sample. Okay. Next, you have fusion. No, fusion is being promoted now as one of the cleanest sample prep procedure. here, what you do is you mix your sample, usually solid sample, with what you call a flux, no, inside the platinum crucible. So the flux is actually a salt. Alright, so some examples. So you have your sodium carbonate, pwede yan. Pwede ring sodium hydroxide, pwede. Pwede rin yung mga borates, no? Lithium borate, okay, lithium borate, sodium metaborate, etc. Now, what you do, no? So nakalagay sa crucible, is you're going to heat up your sample inside a furnace, no? Now, during the heating up, no, inside the furnace, usually high temperatures, no, mga 800 to 1000 degrees centigrade. What happens is that the flux, the salts actually melts. Okay? And what you form here is a liquid, ionic liquid, no? What you form here is an ionic liquid. Okay? Now, the nature of the ionic liquid is quite interesting because it actually eats away your sample matrix. So, again, you're liberating now your analyte, no? And in this case, the metal analyte. So, after the heat treatment, what you usually get is a crystal, no? A crystal that is soluble to, usually, no, just water. So here you don't need to use concentrated mineral acids anymore, no? Just water, you can dissolve the crystal, or a little bit of acid, no, but not as consumptive, no, ng wet ashing or dry ashing. Alright, so that's fusion. Normally, you will encounter fusion sample preps if you're working with cement factories, for example, or geological samples. No, this is where they most likely, no, would use fusion sample prep technique. Okay. Next, you have your solubilization. So solubilization is used for tissue samples, no, biological samples, wherein your analyte is actually trapped inside the cellular matrix. Okay, so you need to liberate your analyte from the cellular matrix. So in solubilization, you are using detergents, no? You are using detergents, usually yung matatawag nating quats, no, or yung quaternary ammonium detergents, no. So this disrupts the cell membrane, and then you can liberate the contents, no, of the cell membrane. So again, this is for biological samples. Next, you have your microwave digestion. So the microwave digestion is just a derivative of the wet ashing method, no. Yung wet ashing kasi, this will usually take around 4 to 6 hours. Ganong katagal ang usual wet ashing. But with the aid of a microwave, no, microwave irradiation, you can do this in around 1 to 2 hours, no. So there are laboratory, hindi yung pambahay na microwave, no. Here you're using laboratory grade microwave digestors, wherein your samples are placed in Teflon tubes. Okay, placed in Teflon tubes. Yeah, so it speeds up the digestion process, no, that typically takes a long time with wet ashing. Next, you have your hydride generation. This is usually used for the analysis of group 5. Yeah, group 5 metalloids or metals. Okay, why? Because compounds like arsenic and antimony, no, they are very stubborn, no. They don't get atomized readily because they tend to form refractory compounds. Okay, so to analyze, they are very they have low volatility, no, yun yung term. So to increase their volatility and to readily transform them into free atoms, what you do is you react them with hydride. Ano ba yung hydride? H negative 1. Okay, so yung sa hydride generator, usually the hydride source is your sodium borohydride, no, from organic chem. Nakilala niyo ito from organic chem. Alright, so here what you do is you convert your arsenic, for example, into the hydride form. And this is very volatile and very flammable. No? So once it gets through the flame, it will be converted now into your free arsenic atoms. No? So it's your hydride generation. It's a separate module, no? So if you're going to buy your own AES, you have to specify if you want to have your own module, no, hydride generation module. Then finally, you have your cold vapor analysis, and this is typically used for mercury analysis, no? Kasi bakit? Mercury is a very toxic metal, okay? In Flame-AAS, if you're going to burn mercury with your flame atomizer, you're just liberating mercury into the atmosphere. Okay? So in cold vapor analysis, what you do is between the light source and the detector, you place your cold vapor setup. No? So it's actually made from a quartz tube. Alright? So from a quartz tube. So here you have your sample containing mercury. Okay, you have an apparatus that blows in air, okay, clean air into the sample. So this allows for your mercury atoms. No, so remember, mercury is liquid in at room temperature rather. Okay, so since it's liquid at room temperature, automatically it has some form of equilibrium with its vapor phase. So here, the air or the gas being pumped is actually pushing mercury vapors out of the solution and into the quartz tube. Okay, so here you don't need to atomize mercury anymore because mercury is now in its free atomic state. No, so the mercury traveling inside the tube will now interact with your radiation coming from your hollow cathode lamp or electrodeless discharge lamp. Then these atoms will be pumped, no, towards a drain, no, wherein there is a some sort of a capturing solution. Okay, so that you will not liberate mercury into the atmosphere. Okay, and you have to dispose of the mercury waste appropriately. All right. So aside from mercury, I think you can also analyze gallium. Yeah, no, you can also analyze gallium, no, using this technique. Okay, so again for metals that are liquid at relatively room temperature. So these are now your sample preparation techniques. So next we have your atomic emission spectroscopy. So in contrast to your atomic absorption, in atomic emission, the analyte itself is the one generating the analytical signal through the emission of radiation. Okay, and this the wavelength of emitted radiation is unique, no, or quite unique per element. So here for atomic emission setups, you don't need to use any light source. Alright. Now, in atomic emission spectroscopy, the analyte or the atom emits radiation due to excitation from the temperature coming from your flame, plasma, or electrical spark or electrical arc. Alright, so this is different from atomic fluorescence spectroscopy. No, I did not include it anymore, no, in this module. But in atomic fluorescence spectroscopy, you need a light source there, no. So the atom, the analyte, also emit radiation, but due to the excitation coming from a light source. Okay, it's quite uncommon, no. Sa Bureau of Plant Industries pa lang yata ako naka-encounter nun, no, or sa fertilizer and pesticides authority. Okay, doon pa lang naka-encounter nito. Usually they use this for the analysis of phosphorus or sulfur. Okay? So medyo bihira siya ma-encounter. Medyo specific yung kanyang application. Okay? Now for atomic emission spectroscopy, this found a widespread application in elemental analysis, no? And most importantly rather, for the determination of sodium, potassium, lithium, and calcium. All of these are easily ionizable compounds, no? So yun yung compounds, elements, no? So yun yung main problem nila, no, with atomic absorption. They get ionized easily. But with atomic emission, before they get ionized, no, or during the ionization step, they emit radiation, and it's the signal that we measure, no, for this technique. If you work during your OJT, if you work with the IRI, International Rice Research Institute, or any related institutions, usually they still have your flame emission spectroscopy, no, or flame emission spectrometers, which are designed to specifically measure sodium and potassium levels, no, accurately. Okay. Again, this is useful, no, for qualitative analysis through comparison of line spectra. Each element will give you a unique line spectrum. Okay, so if you remember the history of yung discovery ng different elements, one of the older methods, no, of confirming whether or not you indeed discovered a unique element, a new element, is by doing emission spectroscopy, no, looking at the emission lines of your element. Okay, so that's the qualitative approach. Again, there's no radiation source. Okay, for emission spectroscopy, it's either the flame, plasma, or electrical arc that will induce excitation of the electrons in the atomic sample. Of course, you still need to use a monochromator and a detector to record the spectrum. In older flame emission spectrometers, okay, they use filters instead. So yung sinabi ko kanina ng mga sodium sa potassium specific flame emission spectrometers, they're actually using filters. All right. Spectral interferences, these are not an issue, no, compared to AAS, because you don't care about the background absorption. No, you're not measuring absorption here. You're measuring emission, and you can pinpoint the emission because you know the wavelength of emission for the particular analyte, no, that you are analyzing. But of course, you still have these non-spectral interferences, no, mga chemical interferences, which we will discuss later. Okay, and one of the common non-spectral interference is what you call your self-absorption, and this is due to the resonance emission lines by unexcited atoms at the surrounding cooler region of the flame. So we'll explain this in more detail later. Shown here is just a comparison of your continuous emission and absorption spectra. Alright, so for the emission spectrum, as you can see, one of the advantages of the emission spectrum is that you get this discrete type of spectra, and the bands, okay, or the emission wavelengths, no, for each element is quite unique. So this is the basis of their identity. Okay, ito yung qualitative information for emission spectroscopy. Okay, so on this slide, we're just going to compare some of the excitation atomization methods. So we discussed this already, atomic absorption. So in relation to the other atomization methods, it's simpler and less expensive. Alright, so yung Flame-AAS nga is just around 2 million or pesos or less, no? So lower operating cost, and somewhat it has greater precision okay, compared to the other atomization methods, and the procedures that uses atomic absorption requires fewer operator skills, no, or lower operator skills. So this is in contrast to what you call your plasma methods, no, such as that for ICP, no, your inductively coupled plasma, no. Yung buong pangalan nun is actually ICP OES, no, inductively coupled plasma optical emission spectroscopy, or atomic emission spectroscopy, no, for other manufacturers, no. So this is the how a plasma looks like. All right, so a plasma is actually generated by feeding it with argon gas. All right, and then argon gas is in turn ionized into a plasma with the help of this RF coil, no. So the radio frequency coil, as well as the magnets, no, the magnetic field inside this coil tube, okay, stabilizes the argon plasma, no. So remember, a plasma is an ionized gas, no, and the temperatures in a plasma can reach up to 10,000 degrees centigrade, no? So very high temperature, and this temperature is, of course, no, very much enough to excite your analyte atoms. Okay, so emission technique ang basis ng plasma methods. Okay, so compared to the arc or spark emission methods, it has a greater reproducibility. Also, spectrometers based on plasma method is designed according to the multiplex design. Okay, so with ICP, you have their instantaneous, no, collection of results. So all the elements present are instantly quantified, no, identified and quantified, no, because of the multiplex design of your ICP system. Okay, then you have your arc and spark methods. So arc and spark methods, you're using these electrodes here. All right, so there are two electrodes, no. So yung the first electrode holds a sample. You can actually analyze here solid samples directly. For plasma methods, you need to convert your samples into solution, no? Solution phase. Okay, so here what happens that each electrodes are electrically biased, no, against a very high voltage difference. So yung sample mo nandito, and what you do is you simply strike, no, the two electrodes with each other, and this creates that electrical arc or electrical spark. So the temperature can reach temperatures, no, up to greater than 10,000 degrees centigrade, no, yung temperature mismo ng electrical spark, and this directly atomizes your sample, and this is very useful for the analysis of refractory minerals, ores, glasses, and alloys without the need for extensive sample pretreatments. Okay, this is not quite common. Isang beses pa lang ako actually naka-encounter nito, no, and it's actually a spark emission spectrometer used for checking yung railroad tracks ng MRT, LRT lines, no? Okay, so you can actually use this, no, for the real-time in situ quality inspection of your railroad tracks, no, yung kung yung integrity ba ng alloy ng railroad tracks remains the same, or nagkakaroon na ba ng structural disintegration, okay, because of oxidation or whatever, no, that causes the railroad tracks to lose some of its components. Okay, yeah, so you have here the different atomization methods for emission. So what are the advantages, no, of your plasma or arc and spark methods? First, you have very low inter-element interferences. Why? Because with plasma or electrical spark, you are already using very high atomization temperatures. Okay, so wala ka ng inter-interference, no, such as in AAS. Okay. Also, because of the multiplex design, you're able to do simultaneous recording of the emission spectra for multi-element samples. No, unlike for AAS, wherein for each element you have to change your lamp, no, yung hollow cathode lamp mo or yung electrodeless discharge lamp mo. Dito you don't need to do that, no, because each element will have its own unique emission spectra, and the detector for the plasma or electrical arc or spark is capable of capturing all of these spectra coming from the different elements simultaneously. Okay. It also allows you for the analysis of elements which are usually impossible for AAS, no, or difficult for AAS, such as boron, phosphorus, tin, uranium, zirconium, niobium. Okay, and this is another unique feature is that you can also directly analyze non-metals, no, such as chlorine, bromine, iodine, and sulfur, which are otherwise not possible with AES, no, yung direct analysis ng non-metals. And compared to your AES, plasma and electrical spark methods have lower LOD, no? So again, lower LOD, better yan, no? So lower LOD, hence higher sensitivity compared to your AES methods. Alright, so that's it for module 8-3. I'm just going to again, no, i-attach ko, i-upload ko lang lahat siguro, no, ng self-assessment forms ng isang bagsakan na lang, no, for all the modules, no, in our Facebook group.